So, what is intelligence really? I mean, it's a question we're all grappling with right now. Today, we're going to dig into a really fascinating attempt to actually pin this concept down, based on the work of Professor Yi Ma. We're going to explore how we can take intelligence from just a fuzzy idea and turn it into a real, solvable scientific problem. You've seen what today's AI can do, right? It can write code, it can make stunning art, it can have conversations that feel, well, real. But all this power brings up a huge question, one that keeps researchers up at night. Are these systems actually understanding the world? Or are they just incredibly sophisticated mimics? Kind of like fancy parrots, just repeating patterns without ever grasping why those patterns exist in the first place. All right, so here's our game plan for this explainer. First, we'll unpack the intelligence puzzle itself. Then we'll dive into two simple principles that Professor Ma suggests are the foundation of it all. We'll use that to explore the difference between just memorizing and truly understanding. Then we'll put today's AI into context with the four big stages of intelligence. And finally, we'll look at what it might take to build the next generation of AI. To really get a handle on what AI can do, and maybe more importantly, what it can't do, we've got to cut through all the hype. It's time we stop talking about intelligence like it's some vague philosophical concept and start treating it like a real scientific problem with, actual math behind it. And that's really the heart of the problem that Professor Maddaleni is tackling. The word intelligence gets thrown around so much it can mean almost anything. If we want to make real, solid progress, we all need to be speaking the same language. We need a formal, scientific way to describe what we're building and how to measure it. We need a blueprint. So, how do you even start building that blueprint? Well, according to Professor Ma, a certain kind of intelligence, the kind that lets us learn, form memories, and build what we call world models, it all rests on two surprisingly simple yet really powerful core ideas. Okay, so you've got these two principles, and they're always working together. Parsimony is all about finding the simplest, most compact pattern you can in a bunch of data. Think of it like hearing a whole symphony and picking out the main melody. But that's not enough, right? That's where self-consistency comes in. It's the quality check that makes sure your simple melody isn't too simple. It has to be good enough that you can use it to reconstruct the entire symphony with all its richness and complexity. And this quote from Einstein just nails it, doesn't it? Professor Marr argues that what Einstein said about science is exactly how intelligence works. As simple as possible, that's parsimony. But not simpler, that's self-consistency. It's this constant push and pull, this tug-of-war, to find the most efficient, but also the most accurate model of reality. So let's zoom in on parsimony for a second. Imagine the world is just a fire hose of messy, complicated data coming at you all the time. Intelligence is the process of taking that fire hose and compressing it down to its absolute essence. It's about finding that hidden structure, those predictable patterns, by filtering out all the noise and chaos. Okay, now that we have this framework of parsimony and self-consistency, let's use it to tackle a huge debate in AI today. What is the real difference between just memorizing something and actually understanding it? So here's the crucial distinction. Simply compressing data isn't the same as figuring out the underlying rules. An AI can memorize the patterns from millions of chess games and get really good at emulating a winning strategy. But does it understand the rules of chess? Does it get why a certain move is necessary? That jump from emulation to necessity is the leap from memorization to genuine understanding. And this is exactly where we see the current limitations of today's large language models. I mean, think about it. Human language is already a super compressed version of our knowledge about the world. So LLMs are basically compressing an already compressed code. Their knowledge isn't grounded in raw sensory data, in sight, sound, touch, the things that build our own internal models of the world. They are absolute masters of emulation, but that's not quite the same as understanding. Now, to really get a sense of how far we still have to go, it's helpful to zoom out and put AI in the grand scheme of how life itself learns. Professor Ma lays out four major stages in the evolution of intelligence. So first, you've got phylogenetic learning. That's the super slow, kind of brutal process of evolution and coding knowledge into DNA. Then a huge leap forward, ontogenetic learning, where a single animal can learn really fast within its own lifetime using its brain and senses. Stage 3 is social learning, sharing all that compressed knowledge through language. And finally, you get to the scientific stage, where we create these abstract systems of logic to discover things that go way beyond what we can just observe. So where does today's AI fit into all this? Well, Professor Ma makes a pretty provocative claim. He says we're basically at stage one. The way we build today's giant models, it looks a lot like evolution. It's a brute force, trial and error process on a massive scale. We try a million different architectures, and the lucky ones survive and become the models everyone uses. It works, sure, but it's incredibly inefficient. Which brings us to the future. What's it going to take to build an AI that can actually leap from that first brute force stage to the higher levels of intelligence, something that looks more like scientific discovery? The path forward really has two big steps. Step one is pretty much what we're all focused on now, getting better at compressing observations of the world into a good solid world model. But step two, that is the real frontier. It's about building systems that can do abstraction, that can form a hypothesis, like two parallel lines never intersect. That's an idea you can't ever prove just by looking at examples, but it's the foundation of deductive logic. So you see, the ultimate goal here isn't to build an AI that can just memorize how humans solve math problems. The goal is to build an AI that understands the necessity of logic so deeply that it could invent brand new mathematical theorems all on its own. It's the difference between reciting a proof and actually creating one. And that really leaves us with the ultimate question, doesn't it? The way we do things now is all about compressing and remixing the huge library of human knowledge. But the next great challenge is to build a system that can write a completely new book for that library, all by itself. Can we build an AI that goes from being a student of humanity to a true scientific peer? Well, that's the journey ahead.